Begin with a single, quiet impossibility. Somewhere in the deepest mathematics we have ever written down for the whole of reality, there is a missing letter. One symbol that ought to be there and is not. The letter is T, the symbol for time, the most fundamental equation we have for the universe, taken as a single object, does not contain it. Stay with me and you will understand why that one missing letter quietly dismantles almost everything you assume about your own life. That tomorrow has not happened yet. That the future is open. That the next moment is genuinely yours to decide. The absence has a consequence. Read the equation literally, and the universe does not flow. It does not unfold. It simply is. Past, present, and future laid out together, complete, finished. Every moment you have ever lived, and every moment you have not yet reached, already exists. Not as a prophecy, as a fixed point in a timeless landscape made of pure mathematics. One physicist gave that landscape a name. He called it Platonia. By the time the screen goes dark, you will understand where the missing time went. Why some of the most serious minds in physics argue your future is already written. Why others insist with equal force that they are wrong. And what it would mean for you and for every choice still ahead of you if the universe is, at its very foundation, made of nothing but math. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins. The trouble starts with a word so ordinary that we almost never examine it. Now, this moment, the present. You feel it as the thin, moving edge where the settled past meets the open future. An edge that slides forward, carrying you with it, second by second, in one direction only. Nothing in your experience is more certain than this. The past is fixed, the future is not yet here, and the present is where you live. Physics does not agree. In 1908, a mathematician named Hermann Minkowski stood before an assembly in Cologne and made an announcement he understood to be radical. He had taken Albert Einstein's young theory of relativity and recognized something hidden inside its equations. Space by itself and time by itself were destined to fade into mere shadows. What was real was the union of the two, a single four-dimensional fabric in which space and time are woven together. We call it space-time. And in Minkowski's picture, that fabric does not come into being moment by moment. It is simply there, all at once, in its entirety. Consider what this means visually. Picture your entire life as a thread. It begins at a point, your birth, and it traces a continuous line through the fabric, through every room you have ever stood in, every street you have walked, every face you have loved. The thread does not have a glowing tip that represents now moving along it. In Minkowski's geometry, the whole thread exists at once, from end to end. The version of you reading these words and the version of you on your last day are both already woven into the cloth. Physicists call this the block universe, and the philosophical position behind it is called eternalism, the claim that past, present, and future are equally real. The reasoning is not mysticism. It comes from one of the most carefully tested facts in all of science: the relativity of simultaneity. Einstein showed that two events which one observer judges to happen at the same moment can happen at different moments for another observer moving relative to the first. There is no universal clock ticking the same now for everyone. Your now and the now of someone walking past you on the street, strictly speaking, slice the fabric of space-time at slightly different angles. And if my present moment can contain events that are still in your future, then those events must, in some sense, already be real. Stretch this logic across the cosmos, and the conclusion follows. There is no single, objective, moving present. The now you trust so completely has no place in the fundamental description. Einstein himself appeared to accept this, and the place he expressed it has become one of the most quoted lines in the history of physics. In March of 1955, learning of the death of his lifelong friend Michele Besso, Einstein wrote to the Besso family. "People like us," he told them, "who believe in physics, know that the distinction between past, present, future is only a stubbornly persistent illusion." Keep that word in mind, illusion. We will return to it and to the circumstances in which it was written, because the circumstances matter more than the quotation alone suggests. For now, hold the picture as the mainstream geometry holds it. The universe is a four-dimensional block. Time is a direction within it, not a river flowing through it. And here is the first foreshadowing seed I will ask you to carry. If the block is the deepest truth, then nothing in it is ever truly decided, because everything in it is already there. We will test that claim carefully before we are done. What does it mean that the most successful theory of space and time we have ever written contains no place for the passage of time? That is not a rhetorical flourish. It is a genuine technical problem, and physicists have a name for it. They call it the problem of time. Hold the phrase, we will earn it. Let us make the abstraction concrete, because abstraction in a vacuum teaches nothing. When Curiosity, NASA's rover, descended toward the surface of Mars in August of 2012, the engineers in the control room at the Jet Propulsion Laboratory faced a delay built into the structure of space-time itself. The radio signal from Mars took roughly 14 minutes to cross the distance to Earth, about 248 million kilometers, some 154 million miles, at that point in the two planets' orbits. By the time the engineers learned the rover had begun its descent, the descent was already, in physical fact, 14 minutes in the past. The landing had either succeeded or failed before they could know which. They sat in a present that was, for the events on Mars, already history. The light had not arrived. The outcome was fixed. Their knowledge of it was not. This is the ordinary daily texture of a universe in which there is no shared now, only the finite speed of light stitching distant events into each observer's personal slice of the block. Into this strange but well-established geometry, one physicist pressed further than almost anyone else has dared. His name is Julian Barbour, and he is one of the more remarkable figures in modern physics, a man who deliberately stayed outside the university system for most of his career, supporting himself by translating Russian scientific journals so that he could think, slowly and without interruption, about the single question that had seized him: the question of whether time exists at all. Barbour's answer took the block universe and removed even the block. In his 1999 book, The End of Time, he proposed that the ultimate arena of reality is not four-dimensional space-time, but something he called Platonia, named deliberately after Plato and his realm of eternal perfect forms. Picture not a film strip of moments following one another, but a vast, timeless landscape. Every possible arrangement of everything in the universe, every possible configuration of every particle, every possible snapshot of reality is a single, motionless point in this landscape. Barbour calls each such snapshot a now. Not the now that moves, a now. A complete, frozen instant, sitting at its own fixed location in Platonia. No more passing or changing than the number 7 changes. In his own words, given to the online forum Edge in 1999, each point in this country is a now, and he calls the country Platonia because it is timeless and created by perfect mathematical rules. There is no track running through this landscape. There is no marker sliding from one now to the next. There are only the nows themselves, all of them, eternally present, like cities on a map that no traveller ever actually visits in sequence. Then where does the overwhelming sense of time come from? The sense of motion, of having a past? Barbour's answer is subtle, and it is the heart of his system. Certain special nows, he argues, contain within them what he calls time capsules, frozen patterns of structure that look exactly as though they are records of a history that led up to them. Think of a single photograph that shows a runner mid-stride, muscles tensed, 1 foot off the track, droplets of sweat caught in the air. The photograph does not move. Nothing in it flows. Yet, locked into that one static image is the unmistakable appearance of motion, of a before and an after. Barbour proposes that your present moment is exactly this, a single static now, stuffed with apparent memories, apparent records, apparent traces of a past, none of which are actually being lived through, because nothing is being lived through. There is only the arrangement, sitting at its point in Platonia, complete. Picture it one more way. Consider a deck of cards in which Every card is a photograph of the universe at some configuration. Shuffle the deck however you like. The cards do not change. Barbour's claim is that reality is the entire deck at once, scattered across Platonia, not a hand being dealt one card after another. The feeling that a card is being turned over right now is, on this view, just what it is like to be one particular card that happens to contain the image of a hand reaching for the next. I want to be careful and fair here because this is a serious idea held by a serious physicist, and we are still only describing it, not yet weighing it. Barbour is not a mystic. His more recent work, the 2020 book, The Janus Point, is dense with hard mathematics, and in 2014 he published, with his collaborators Tim Kozlowski and Flavio Mercati, a peer-reviewed paper in Physical Review Letters, arguing that the arrow of time, the very sense that things run from order toward disorder, can emerge from a system that has no built-in direction at all. In their model, a simple gravitating system of particles with no special starting condition naturally divides at a single point of minimum complexity into two halves, and in each half a measure of structure grows in opposite time directions, like two rivers flowing away from a single mountain spring. They call it the Janus Point, after the two-faced god who looks both ways. We will come back to what this does and does not establish. For now, notice the shape of the claim and let it sit with you. The theory proposes that the flow of time is not fundamental. The theory proposes that your past is not behind you, but beside you, frozen at its own address in a timeless landscape. The theory proposes that you are not traveling through your life at all, that the sensation of travel is a feature baked into a single still frame. These are presented as the consequences of taking the mathematics seriously. Whether the mathematics should be taken that seriously is a separate question, and a question we will hold for later. There is a second great idea moving beneath all of this, and it is even more radical than the disappearance of time. It is the question of what the universe is ultimately made of. Not what it contains, particles, fields, galaxies, but what it is at the deepest level. The standard, comfortable answer is that the universe is made of physical stuff, and that mathematics is the language we humans invented to describe that stuff. The equation is the map. The territory is something else, something material, something real in a way that the map is not. A cosmologist at the Massachusetts Institute of Technology, named Max Tegmark, has spent his career arguing that this comfortable answer is exactly backwards. Tegmark's proposal is called the mathematical universe hypothesis. He builds it from a starting point that sounds modest. He calls it the external reality hypothesis, the assumption that there exists a physical reality completely independent of us human beings, a reality that would still be there if every conscious mind vanished. Most scientists accept something like this without a second thought. But Tegmark argues that if you accept it and follow the logic without flinching, you are driven to a startling destination. A reality that exists completely independently of human minds must be describable in a way that is completely free of human baggage, free of language, free of the particular concepts our particular brains happen to use. And the only kind of description that has that property, he argues, the only language with no human fingerprints on it, is pure mathematics. From which Tegmark draws his conclusion. Physical reality is not merely described by mathematics. Physical reality is a mathematical structure. The universe does not obey mathematical laws. The universe is mathematics, in the same way that the number 7 is not made of anything more basic than itself. Writing in Scientific American in 2014, drawing from his book Our Mathematical Universe, Tegmark put the implication as bluntly as it can be put. If you believe in an external reality independent of humans, he wrote, then you must also believe that our physical reality is a mathematical structure, and that everything in our world is purely mathematical, including you. Not a being described by mathematics, a mathematical object, no more and no less. Set Tegmark's claim beside Barbour's, and you can feel the two ideas locked together into something larger and stranger than either alone. Barbour says reality is a timeless landscape of frozen nows. Tegmark says reality is, at bottom, a mathematical structure. Put them together, and you arrive at the full picture this exploration is named for. A timeless universe in which your entire future already exists, not metaphorically, not poetically, but literally, as a region of an eternal mathematical object. Platonia, where the future is not coming, because, in the language of pure mathematics, there is no coming. There is only what is. But notice, and I want you to notice it now, quietly, because we will need it later, that Tegmark has made a move. He has slid from being described by mathematics to being mathematics, as if the two were the same thing. Is being described by math the same as being made of math? Hold that question. Do not answer it yet. We are still only laying out what is claimed. The examination comes later, and when it comes, it will begin precisely here. What does it mean that a respected cosmologist can argue in the pages of a mainstream science magazine that you are a mathematical structure? At minimum, it means we have wandered far from common sense and far from the laboratory, into territory where the usual tools of physics, the experiment, the measurement, the prediction, begin to lose their grip. Keep that in mind as well. We will need it. Let us put some hard numbers on the stage, because this channel does not deal in vague awe, and because the precision of the numbers will matter enormously before we are finished. The universe, as measured by the European Space Agency's Planck satellite and announced in March of 2013, is 13.82 billion years old. The mission's scientists stated it plainly. The data imply that the age of the universe is 13.82 billion years. The smallest meaningful length in physics, the Planck length, is about 1.6 times 10 to the minus 35 meters, roughly 5 times 10 to the minus 35 feet. a scale so far below anything we can probe that it makes an atom look like a galaxy. The corresponding Planck time is about 5 × 10⁻⁴ seconds. And the number of particles in the observable universe sits somewhere near 10 to the 80th, a 1 followed by 80 zeros. Carry these numbers lightly for now. One of them, before the end, will grow into something that no human mind can hold. Here is where the abstraction acquires its full weight, and where the problem of time stops being a phrase and becomes a wound in the heart of physics. To see it, we have to look at the equation with the missing letter, and understand why its absence is not a clerical error, but the deepest puzzle in the foundations of physics. To do that, we have to descend from the comfortable surface of relativity into the strange machinery underneath, where the universe is treated not as a landscape we look at, but as a single quantum object with a single wave. That descent is where we go next. To find the missing letter, we have to change how we look at the universe. Until now, we have pictured it as a landscape, a block we view from outside, a map of space-time spread before us. But there is another way to write the laws of physics, an older way. And when you apply it to gravity, something disturbing happens. The method is called the Hamiltonian formulation, and it is the natural language of quantum mechanics. Instead of describing the whole four-dimensional history at once, you slice the universe into a stack of three-dimensional moments, a now for the whole cosmos, and you write equations that tell you how to move from one slice to the next. It is the physics of evolution, of one state giving rise to the following state. It is built from the ground up around the idea of marching forward in time. When physicists applied this slicing method to Einstein's general relativity, they ran into a wall that has defined the field ever since. General relativity has a peculiar feature. It does not care how you slice it. You can carve the four-dimensional block into nows in any way you like, at any angle, and the physics must come out the same. This freedom, whose technical name is diffeomorphism invariance, sounds harmless. It is not. It means that the labels you attach to your slices, including the label time, are not physically real. They are bookkeeping. And when you write down the equation that enforces this freedom, an equation called the Hamiltonian constraint, it takes a startling form. It says, in effect, that a certain total quantity for the whole universe must equal 0. In the classical theory, you can write it as H is approximately 0. The energy that would drive the universe's evolution forward, taken globally, vanishes. Now take the final step. Take that constraint and do to it what quantum mechanics demands. Turn it into an equation for a wave. In ordinary quantum mechanics, every object, an electron, an atom, is described by a wave function, a mathematical object that encodes everything that can be known about it. John Wheeler, the same physicist who coined the terms black hole and wormhole, proposed in 1957 that the entire universe could be described by a single such wave, a wave function of the universe, living not in ordinary space, but in an abstract arena he called superspace, the space of every possible shape the universe could have. And in 1967, the physicist Bryce-DeWitt wrote down the equation that this universal wave must obey. It is the equation with the missing letter. We call it the Wheeler-DeWitt equation, and in its compact form it reads h hat psi equals 0. Let me give you each piece in plain language. H hat is the Hamiltonian operator, the mathematical machine that, in ordinary physics, generates change over time. Psi, the Greek letter, is the wave function of the entire universe, the single mathematical object that encodes every possibility for everything. And the right-hand side is 0. The equation says that the machine which generates time, applied to the universe as a whole, gives nothing, stillness. The wave function of the universe does not change because there is no external time with respect to which it could change. To feel how strange this is, set it beside the equation it grew out of. The central equation of ordinary quantum mechanics is the Schrödinger equation. I h bar, the partial derivative of psi with respect to t, equals h hat psi. You do not need to follow the symbols to see the one thing that matters. On the left sits that letter, t, time, explicit, essential, the variable with respect to which the whole quantum state evolves. The Schrödinger equation is a story about how things change from one moment to the next. Now look again at the Wheeler-DeWitt equation. The t is gone. In the passage from the physics of objects within the universe to the physics of the universe itself, time has quietly dropped out of the mathematics altogether. This is not a fringe reading. The physicist Carlo Rovelli, one of the founders of an entire approach to quantum gravity, has stated it without hedging. In the quantum gravity equation par excellence, the Wheeler-DeWitt equation, he writes, there is no time variable t at all. None. The deepest equation we have for the cosmos describes something that does not, in any straightforward sense, happen. What does it mean that the equation for everything has no time in it, and that the physicists who wrote it cannot, even now, fully agree on how the time we so plainly experience climbs back out of it? That is the problem of time, stated at last in its full force. And notice the foreshadowing seed planted in the very structure of the difficulty. If the fundamental equation is frozen, then the flow you feel is not in the fundamental equation. It is something added, something emergent, something that the deepest layer of physics does not itself contain. Whether that absence points toward a universe that is genuinely timeless, or merely toward a theory that is genuinely incomplete, is a question we are deliberately leaving open for now. I should be honest about the status of this equation because fairness demands it. The Wheeler-DeWitt equation is not a polished, fully understood law like the equations of electromagnetism. It is, in the general case, mathematically ill-defined, a notorious tangle that physicists can only solve in drastically simplified toy models called mini-superspace, where you pretend the universe has just a handful of features. DeWitt himself, by several accounts, came to dislike the equation that bears his name and the fame it brought. Wheeler, by contrast, was captivated by it. The equation is a milestone and a mystery, at once taken seriously enough to build careers on, understood poorly enough that its central feature, the absence of time, remains genuinely unexplained. Both of those things are true, and we will need both. If the universe's fundamental state is frozen, you are left with the obvious question. The question of why you feel time passing at all. And here, the physics offers an answer so elegant and so unsettling that it has been demonstrated in a laboratory with particles of light. The answer is called the Page-Wouters mechanism, after the physicists Don Page and William Wouters, who proposed it in 1983. Their insight begins with quantum entanglement, the strange linkage by which two particles can share a single joint state, so that neither has a definite property on its own, yet together they are perfectly correlated. Page and Wouters asked what would happen if the universe is globally frozen, exactly as the Wheeler-DeWitt equation says, but inside it, one part plays the role of a clock, and that clock is entangled with everything else. Then, they showed, an observer who is part of the system, who reads the clock from the inside, will see the rest of the universe evolving, ticking, changing, flowing, even though the universe as a whole, viewed from some impossible outside vantage, never changes at all. Time, on this view, is not a fundamental backdrop. It is a relationship, a correlation between a clock and the world, read from within. Think of it this way. Picture a single, motionless photograph of a clock tower, with a long boulevard stretching away beneath it. The photograph does not move. But suppose that within the single image, the position of the clock's hands is perfectly correlated with the positions of everyone on the boulevard. When the hands point one way, the crowd is bunched near the tower. When they point another, the crowd has spread toward the horizon. Nothing in the photograph is moving. Yet, locked inside that one frozen image is a complete, consistent story of motion, readable by anyone who uses the clock hands as their index. The Page-Wouters claim is that your experience of a flowing universe is exactly this: the inside view of a static, entangled whole indexed by a clock that is itself just another frozen part of the picture. And this is not only philosophy. In 2013, a team led by Ekaterina Moreva at the Italian National Meteorological Institute in Turin built a small concrete version of it using entangled photons. They prepared a pair of photons in a joint state, used one as a clock and the other as the system, and showed that an observer who correlated the two would record the system as evolving in time, while an external super-observer, measuring the global state all at once, would find it static and unchanging. Time, in their photonic toy model, was not in the equations. It emerged from the entanglement. The experiment does not prove that our universe works this way. It illustrates that the mechanism is coherent, that a static whole can contain inside itself the genuine appearance of flow. Hold that distinction illustrates, not proves, because it will matter when we begin to weigh these ideas rather than merely describe them. If the disappearance of time troubles you, the next idea should trouble you more, because it comes not from speculative quantum gravity, but from an exact solution to Einstein's own equations. and it was a birthday present. In 1949, for Albert Einstein's 70th birthday, his friend and colleague at the Institute for Advanced Study in Princeton, the logician Kurt Gödel, perhaps the greatest logician since Aristotle, presented him with a gift unlike any other. Gödel had found a new, exact solution to the Einstein field equations. Those equations, the core of general relativity, can be written g mu nu plus lambda g mu nu equals 8 pi g over c to the fourth times t mu nu. In plain language, the left side, the g mu nu term, describes the curvature of spacetime, how it bends. Lambda is the cosmological constant, a tension built into space itself. And the right side, T mu nu, describes the matter and energy doing the bending. The equation says, in Wheeler's own famous summary, that matter tells spacetime how to curve, and curved spacetime tells matter how to move. Gödel's solution described a possible universe, not necessarily ours, but one that Einstein's equations permit, that is, uniformly rotating, the entire cosmos slowly turning. And in such a universe, Gödel proved something that should be impossible. The rotation drags the very fabric of space-time around with it so violently that, far enough from any point, the light cones, the structures that define future and past, tip over completely on their sides. Follow the tipped cones, and you can trace a path through space that is always, locally, heading into your own future, and yet arrives back at your own past. A closed loop in time, a closed time-like curve. In Gödel's universe, you could, in principle, travel into yesterday. Picture it. You set out, never once reversing direction, always moving forward through your own local time, the way you move forward through every ordinary day, and the geometry of a rotating cosmos curves your path around until you arrive at the morning of your departure, with your earlier self still there. This is not a wormhole, not exotic engineering. It is a direct consequence of Einstein's equations applied to a spinning universe. There was a reason a logician would give a physicist a universe with time loops for his birthday. Gödel was making an argument, and the argument was philosophical. Gödel was, in the words of Bertrand Russell, an unadulterated Platonist, a man who believed that mathematical objects, the integers and their truths, are as real as tables and chairs, and that they exist in a timeless realm we discover rather than invent. And Gödel believed deeply that the passage of time is an illusion. His rotating universe was his proof of concept. In a companion essay written that same year, he reasoned that if a universe is possible, permitted by the laws of physics, in which you can revisit the past, then the past cannot have genuinely passed away into non-existence. It must still be there to be revisited. And if time's passage is not a necessary feature of every physically possible world, then, Gödel argued, it is not a fundamental feature of reality at all. It is something about us, not about the cosmos. I must be fair about the physics. Gödel's rotating universe is almost certainly not our universe. We observe no such cosmic rotation, and the solution has features that do not match the cosmos we see. It is what physicists call unphysical, mathematically exact, but not a description of reality. Yet it has never been dismissed, because it makes a point that cannot be unmade. Einstein's own equations, the bedrock of modern cosmology, do not forbid travel into the past. The laws permit it. And a theory of time in which time loops are permitted is a theory in which the simple story, past gone, future not yet here, was never written into the foundations. When I first sat with Gödel's birthday gift, what unsettled me was not the time travel. It was the quiet confidence of a man who believed, on the strength of a single equation, that the moment he was living in did not truly pass away. I return to that often, not because it comforts me, but because it shows how far a mind will follow a formula, even past the edge of the world it can actually see. There is a deeper current still running beneath all of this, and it carries us toward the idea that reality may be, at its root, not matter, not even geometry, but information. In the early 1990s, the physicist Gerard 't Hooft and then Leonard Susskind proposed something they called the holographic principle. It grew out of a fact about black holes discovered by Jacob Bekenstein and Stephen Hawking, that the amount of information a black hole can contain is not proportional to its volume, as you would expect, but to the area of its surface. We can write the relationship as the Bekenstein-Hawking entropy. S equals kc cubed A over 4g h bar. In plain terms, the information content, S, of a black hole is set by A, the area of its event horizon, measured in units of the Planck area, roughly 1 bit of information for every tiny square of space about a Planck length on each side. Not the volume inside, the surface around. Think of what that implies. If the maximum information in any region is fixed by its bounding surface rather than its interior, then, in some precise sense, everything happening inside a volume of space can be encoded on its boundary, the way a flat hologram encodes a three-dimensional image. Susskind put the consequence starkly in a 1994 paper titled "The World as a Hologram." The three-dimensional world of ordinary experience, the principle suggests, may be a kind of projection of information written on a distant two-dimensional surface. This idea found its most powerful expression in 1997, when the Argentine physicist Juan Maldacena published a precise mathematical version of it, a correspondence showing that a theory of gravity in a certain curved space is exactly equivalent to a theory without gravity living on that space's boundary. The schematic statement is that a gravitational theory in the bulk equals a quantum field theory on the boundary. To convey how seriously the physics community took this, Maldacena's paper has been cited more than 22,000 times. By the count of the Inspire High Energy Physics database, 22,256 citations, making it, by a wide margin, the most cited paper in the history of high-energy physics. The field staked its attention on the proposition that space-time itself might be emergent, woven out of something more fundamental. And there is an answer taking shape for what that something is. Increasingly, the answer offered is entanglement and information. In 2013, Maldacena and Susskind proposed a conjecture they wrote as a kind of equation between abbreviations, that a wormhole connecting two regions, which physicists label ER after a 1935 paper, is the same thing as quantum entanglement between them, labelled EPR after another. ER equals EPR. Entanglement, on this view, is not merely a correlation between distant particles. It is the very thread out of which the connectivity of space is sewn. Susskind has summarized the vision in a single sentence. Space-time is a form of quantum entanglement. Wheeler, near the end of his life, gave this entire direction its slogan. He called it from bit. Every item of the physical world, he wrote in 1989, has, at bottom, an immaterial source and explanation. What we call reality arises from the posing of yes or no questions. All things physical are, at root, information theoretic in origin. It from bit. Reality, on Wheeler's reading, is not made of stuff that happens to carry information. It is made of information, and the stuff is how the information looks from inside. Lay these pieces side by side, and a single, audacious picture assembles itself. Time is absent from the deepest equation. The flow we feel may be the inside view of a static, entangled whole. Space itself may be emergent, a projection of information on a boundary. And reality at its root may be informational, which is to say, mathematical. Each of these is a respected line of research. Together, they sketch a cosmos that looks less like a vast machine grinding forward through time, and more like a single, timeless mathematical structure, the source code, if you like, of Platonia. This is the strongest case for the timeless mathematical universe, and I have tried to state it at full strength, because an argument is only worth examining once it has been made as powerful as it can be made. But physics is not a chorus, it is an argument, and against this entire picture stands one of the most forceful dissenters in the field. And his objection is the mirror image of everything we have just built. His name is Lee Smolin, and he says flatly that time is real, the most real thing there is, and that the timeless universe is the deepest mistake in modern physics. Smolin, a founder of the Perimeter Institute for Theoretical Physics, argues in his 2013 book, Time Reborn, that physicists have fallen in love with their own timeless equations and mistaken the map for the territory. Whatever is real in our universe, he writes, is real in a moment of time, which is one of a succession of moments. The past was real, but is no longer real. The future does not yet exist and is therefore open. Nothing, he insists, not even the laws of nature, transcends time. For Smolin, the experience you have of living in the present moment is not an illusion to be explained away. It is the deepest clue we have to the fundamental nature of reality. And a physics that throws it out has thrown out the evidence. And Smolin does something the timeless camp struggles to do. He makes a prediction you can test. In his 1997 book, The Life of the Cosmos, he proposed a startling idea he called cosmological natural selection. Suppose, he said, that new universes are born inside black holes. that every black hole that forms buds off a baby universe on the far side of its singularity. Suppose further that each baby universe inherits the physical constants of its parent, but with slight random variations, like offspring inheriting genes with small mutations. Then, over countless generations, the population of universes would be dominated by those whose constants are best tuned to produce black holes. Because black holes are how universes reproduce. Our universe's apparently fine-tuned constants on this view would not be a cosmic coincidence and would not require a designer. They would be the outcome of a long lineage, selected, like biological traits, for fertility. Whatever you make of the idea, notice what makes it scientifically respectable. It sticks its neck out. Cosmological natural selection predicts that our universe should be near optimal for making black holes, and that has a sharp, falsifiable consequence. The most massive kind of star that collapses into a black hole sets a limit. If our constants were tuned to maximize black hole production, then the maximum possible mass of a neutron star, the dense stellar core that sits just below the threshold of collapse, should fall right around 2 times the mass of our Sun. Make a neutron star much heavier than that, Smolin argued, and his theory would be in serious trouble. So the test became a hunt for heavy neutron stars. And in 2010, using the Green Bank telescope in West Virginia and a precise timing technique that exploits the way the star's gravity delays the radio pulses passing near it, a team led by Paul Demarest measured the mass of a pulsar with the catalogue name PSRJ 1614-2230. The result, published in the journal Nature in October of 2010, was 1.97 times the mass of the Sun, give or take 4/100ths. At the time, it was the most massive neutron star ever weighed, and it sat almost exactly at the edge Smolin's theory had drawn. Not over it, at it. The prediction survived its most dangerous test. I tell you this not because cosmological natural selection is proven. It remains very much a minority view, and its central mechanism of universes budding inside black holes is undeveloped. I tell you because it shows what it looks like when the time is real camp does its work. It makes a claim that reality could have falsified, and reality, so far, did not. What does it mean that the camp which insists time is real is also the camp willing to be proven wrong, while the camp that calls time an illusion offers nothing an experiment could ever touch? Hold that asymmetry. We will need it when the time comes to weigh these visions against each other rather than merely admire them. Between the frozen block and Smolin's flowing time stands a third figure, trying to hold both truths at once. The South African cosmologist George Ellis, a man serious enough that he co-wrote with Stephen Hawking the foundational 1973 textbook on the large-scale structure of space-time, has proposed what he calls the evolving block universe. Ellis accepts that the past is fixed, laid down, as solid as the eternalists say. But he denies that the future is. In his picture, space-time is not a finished four-dimensional block. It is a block that grows. The present is a real, advancing boundary, the surface where, in his phrase, the potential of the future is continually converted into the certainty of the past. Behind that surface, the block is fixed and definite. Ahead of it, there is nothing yet. The future is open, not laid out, not waiting. Reality, on Ellis's view, is the growing block, accreting new, fixed past at the moving edge of an open present, like a crystal slowly adding layers, or like a recording being written that can never be unwritten but is not yet finished. Ellis is blunt about why he resists the frozen picture. The static block, he argues, is in profound contradiction with the world we actually inhabit, with chemistry, with biology, with the irreversible flow of ordinary life, in which eggs break but do not unbreak, and the dead are not restored. A theory that declares all of that an illusion, he suggests, has not solved the problem of time so much as renamed it. We will weigh that charge directly before we are through. There remains one more thinker we must bring into the room, because his work cuts in a direction all its own, and it will become central when we turn from describing these ideas to examining them. Roger Penrose, mathematician, physicist, winner of the 2020 Nobel Prize, is, like Gödel, a committed mathematical Platonist. He speaks of a timeless Platonic world of mathematical truth as, in a sense, the most fundamental of all realities. But Penrose has spent decades arguing for something that sits in deep tension with the idea that we, and our minds, are merely pieces of computable mathematics. His argument reaches back to Gödel. In the 1930s, Gödel proved his incompleteness theorems, which showed that in any consistent formal system, rich enough to do arithmetic, there are true statements that the system itself can never prove. Penrose, in his 1989 book The Emperor's New Mind, and its 1994 successor, Shadows of the Mind, takes this further than most mathematicians will follow him. Human mathematicians, he argues, can see that such a statement is true, can step outside the formal system and grasp a truth the system cannot reach. But a computer is a formal system. It can only grind through the rules it is given. Therefore, Penrose concludes, human mathematical understanding is not computation. There is something the mind does that no algorithm, no machine, no piece of running software can do. He links this non-computable element of mind to a proposed form of quantum collapse in the brain. And he is candid that these ideas are speculative. But the core claim is stark, and we will need it. If Penrose is right, then you are not a computable mathematical structure, because your understanding outruns computation itself. Penrose has pushed his Platonism out to the largest scale as well. In his 2010 book, Cycles of Time, he proposed conformal cyclic cosmology, the idea that our universe is one of an endless sequence of eons, each one's far future smoothly continued into the next one's Big Bang. He has claimed to see faint evidence of the previous eon imprinted in the cosmic microwave background, in the form of concentric circles and so-called Hawking points. I will be straightforward, because intellectual honesty requires it. Those claims are contested. Independent reanalyses, one by Zhao and Scott in 2019, and a larger study in 2024, found no statistically significant evidence for the Hawking point signal in the data, once the proper comparisons were made. Penrose continues to defend the theory. Most cosmologists remain unconvinced. I include it not as established fact, but as a caution we will need later, a reminder of how easily a beautiful mathematical vision can outrun the evidence meant to support it. And there is one last shadow gathering at the edge of all these timeless and infinite cosmologies, which I will name now and return to with full force. In any universe that lasts long enough, or contains enough randomness, and several of these models do, there is a disquieting statistical consequence. Given enough time, random fluctuations could assemble, out of disordered chaos, a single conscious brain, complete with false memories of a life and a world that never existed, lasting only a moment before dissolving back into noise. Physicists call such a thing a Boltzmann brain. And the trouble is that in certain timeless and eternal models, these momentary, randomly assembled observers are predicted to vastly outnumber observers like us, who evolved from an orderly past. Keep that prediction in mind. When we return to it, it will not be a curiosity. It will be a blade we turn against the theories themselves. What does it mean that the deepest pictures physics can draw of reality split at their foundations into two opposed visions? One in which your future already exists, frozen and complete, and one in which the future is genuinely open, and the present moment is the realest thing there is, and that the choice between them cannot, at present, be settled by any experiment. It means we have reached the limit of what description alone can give us. We have laid out the timeless universe at full strength, and the case against it at full strength. Everything until now has been the defense, the fair, patient hearing. Now the work changes. Now we examine. Now we ask not what these theories say, but whether what they say can bear the weight that some have tried to place upon it. Let us begin the examination where the boldest claim was made. Tegmark told us that physical reality is not described by mathematics, but is mathematics, and that you, therefore, are nothing but a mathematical structure in a cosmos that needs no maker because it simply exists the way the number 7 exists. This is the claim that does the most metaphysical work, and so it deserves the most careful cross-examination. Let us give it its strongest form first, as we promised we would. The strongest form is this: mathematics is unreasonably effective. The physicist Eugene Wigner gave that phrase to the uncanny way abstract equations, invented in one century for their own sake, turn out to describe the physical world with pinpoint accuracy in the next. Why should reality bend so perfectly to our equations, unless, as Tegmark says, reality simply is those equations? It is an elegant thought. It explains the effectiveness of mathematics by erasing the gap between the math and the world. There is no gap because there is no difference. Now we examine, and the first crack appears at exactly the place I asked you to mark long ago in the opening. Tegmark slid from a defensible claim that the universe is described by mathematics to a far stronger one, that the universe is mathematics. Those are not the same claim. The physicist Sabine Hossenfelder, no friend of religious argument, puts the objection with precision. That the world is math, rather than merely being described by math, she notes, is an additional assumption, and not a small one. A perfect map of a city is not the city. A flawless equation describing a waterfall does not get you wet. To describe something completely is one achievement. To be that thing is another entirely. And no amount of descriptive success closes the distance between them. Tegmark needs that distance to vanish, and asserting that it vanishes is not the same as showing that it does. Press harder, and a second problem surfaces, one that proponents themselves concede. If all mathematical structures exist physically, as Tegmark's hypothesis requires, then our universe is just one structure among an infinite ensemble of them, the overwhelming majority of which would be vastly more complicated, more arbitrary, more chaotic than ours. So why do we find ourselves in one of the rare, clean, elegant, law-abiding structures? A universe simple enough that a handful of equations capture it, rather than in one of the infinitely more numerous monstrosities. Tegmark has no settled answer. This is a version of what cosmologists call the measure problem, the impossibility of even defining what typical means across an infinite ensemble. And here is the admission that matters, in Tegmark's own words about his refined proposal. It faces, he writes, serious challenges, including the awkward fact that virtually all historically successful theories of physics violate it. Read that again. The man's own theory, by his own admission, is in tension with virtually every theory of physics that has ever actually worked. When the architect tells you the foundation does not match the building, you do not need an outside critic to worry. And there is a third examiner, the most damaging of all, because it questions not whether the theory is true, but whether it is even a scientific theory. The mathematician Peter Woit, reviewing Tegmark's program, concluded that its problem is not that it is wrong, but that it is empty, radically untestable. George Ellis, the cosmologist we met earlier, reached the same verdict from the inside of the field. An infinite ensemble of disconnected mathematical universes is, he wrote, completely untestable. No observation we could ever make would distinguish a universe that merely obeys mathematics from one that is mathematics. No experiment could confirm or deny the existence of the other structures in the ensemble, because they are, by construction, causally cut off from us forever. We have left the territory of physics, where claims answer to measurement, and entered the territory of metaphysics, a metaphysics dressed in the vocabulary of physics, which is a different and more deceptive thing than honest metaphysics openly declared. So let us ask the question the theory cannot answer, and let us ask it plainly. Where does the mathematical structure get its existence? A circle does not draw itself. The number 7 does not bring itself into being, sustain itself, or do anything at all. It is abstract, inert, causally powerless. It cannot cause anything, because causation is something that happens in time to things with the power to act, and a mathematical object has no such power. So even if you grant, for the sake of argument, that reality is a mathematical structure, you have not explained why that structure is instantiated. You have not explained why it is real, lived, burning with actual existence, rather than merely a possibility sitting unrealized in the space of all possible structures. An equation on a page does not make a universe. Something must breathe fire into the equations, as Stephen Hawking once memorably wondered, and make a world for them to describe. The mathematical universe hypothesis does not answer that question. It hides it by quietly assuming that mathematical existence and physical existence are the same, the very assumption Hossenfelder flagged. Strip away that assumption, and the theory does not eliminate the need for a cause of the universe's existence. It relocates the need, dresses it in equations, and hopes you will not notice that the deepest question, why is there a real world at all, rather than just the timeless possibility of one, has been smuggled past you unanswered. Here is the inversion at the heart of it. Tegmark presents mathematics as the great solvent of mystery, the thing that lets us dissolve God into equations. But examine what mathematics actually is, on his own telling. A realm of perfect, eternal, immaterial truths, existing independently of all physical things, ordering and governing the cosmos with flawless precision. A timeless, non-physical source of all order, in which the physical world participates, and from which it derives its structure. That is not an argument against a transcendent, intelligent cause. That is very nearly a description of one, minus the mind. The mathematics does all the work that an intelligent cause would do. Tegmark simply declines to ask why such a realm of ordering truth should exist, or why it should be lit into actuality as a real and living cosmos. The equations point upward, toward a timeless source of order. He has merely refused to follow where they point. Now let us turn to the second claim, the one wheeled in to answer the most uncomfortable fact in all of cosmology. The fact is fine-tuning. And before we examine the response to it, we must let the fact itself land with full weight, because everything turns on its magnitude. The universe is built on a small set of numbers: the strength of gravity, the energy of empty space, the conditions at the very beginning. And these numbers are set to a precision that has no parallel in ordinary human experience. Consider just one: the cosmological constant, the energy density of the vacuum, the lambda in Einstein's equation. The value we observe is smaller than the value that the most basic physics would naively predict, by a factor with roughly 120 zeros after it. To put that another way, the vacuum energy is balanced, cancelled, tuned to about 1 part in 10 to the 120th power. And consider a second number, identified by Roger Penrose. The precision of the universe's initial low-entropy state, the orderly condition the cosmos had to begin in for any structure, any star, any life ever to be possible. Penrose calculated that precision at 1 part in 10 raised to the power 10, raised again to the power 123. I need you to feel that number, not just hear it. So let me try to make it visible. The exponent alone, 10 to the 123, is a number with more digits than there are particles in the entire observable universe. There are roughly 10 to the 80th particles in all of space, every atom, in every star, in every galaxy. The exponent of Penrose's number dwarfs even that. You could not write the full number out. There is not enough matter in the cosmos to make the ink, not enough surface to hold the digits. This is the degree of precision built into the starting conditions of reality. Now picture what such precision means. Imagine a control panel, vast beyond imagining, covered in dials. And to set the universe running as ours runs, each dial must be turned to one exact setting out of a number of possible settings so large it cannot be written down. Not approximately, exactly. Turn any one of them a hair in either direction, and there are no stars, no chemistry, no carbon, no observers, nothing. A dead or formless cosmos. And these are not dials we watched anyone set. They appear to have come from the beginning, already at their precise, life-permitting values. This is the fact. Even physicists who want no part of any theological conclusion grant the fact. They argue only about what it means. What does it mean that the universe's foundational numbers are tuned to a precision of one part in a number too large to write? That is the question fine-tuning forces. And the most popular naturalistic answer, the answer wheeled in precisely to avoid the conclusion that precision implies a decision, is the multiverse. If there exist vast numbers of universes, the argument runs, each with randomly different constants, then somewhere in that immense lottery, a few will happen to hit the life-permitting values by chance. And of course, we find ourselves in one of those, because we could not exist anywhere else. The fine-tuning is not designed. It is selected after the fact by our own existence. No tuner required. Let us give that its fair hearing, and then let us examine whether it survives. It is a serious proposal, advanced by serious physicists. André Linde, Alan Guth, Leonard Susskind, and Tegmark himself, often grounded in the theory of eternal inflation, which generically produces an endless froth of bubble universes. But the proposal carries inside it three flaws that its own advocates have been forced to confront. The first is the measure problem, and it is fatal in a quiet, technical way. To say that most universes are lifeless, and a few permit life, and we are in one of the few, requires you to count universes, to define what fraction of an infinite ensemble has this or that property. But you cannot consistently count an infinity of universes. The fractions come out as infinity divided by infinity, which can be made to equal almost any answer you like, depending on how you slice the counting. The cosmologists Guth, Linde, and Vilenkin, among the founders of inflationary cosmology, have acknowledged that this measure problem may be, in their phrase, the Achilles heel of eternal inflation. The very framework offered to explain fine-tuning cannot at present even define the probabilities on which its explanation depends. The second flaw is the one I asked you to keep in mind: the Boltzmann brain. In an eternal, infinite multiverse, random fluctuations will, over unlimited time, produce isolated conscious observers, brains complete with false memories, and the mathematics of several such models predicts that these momentary, randomly assembled minds vastly outnumber observers like us, who arose from an orderly cosmic history. And now follow the logic to where it goes, because this is the move the physicist Sean Carroll made in 2017, and it is a thing of terrible beauty. If a theory predicts that you are overwhelmingly likely to be a Boltzmann brain, a momentary fluctuation hallucinating this entire world, including all the evidence and reasoning that led you to the theory, then the theory has sawed off the branch it is sitting on. For if you are a Boltzmann brain, your memories are false, your reasoning is random noise, and you have no grounds to trust the very observations and logic that led you to believe the theory in the first place. Carroll's verdict is precise. Such a theory is cognitively unstable. It cannot simultaneously be true and justifiably believed. A theory that, taken seriously, destroys your reason to believe it, has refuted itself. This is the multiverse turned, by its own internal logic, into a reductio against itself. What does it mean when the leading naturalistic answer to fine-tuning, taken seriously, leaves you no rational ground to trust the very mind that reasoned its way to the answer? Sit with that for a moment before we go on. A theory that soars through its own support is not a rival explanation. It is a warning. And the third flaw is the one that exposes the whole maneuver. We have never observed another universe. We cannot, even in principle. They are causally disconnected from us, sealed away forever beyond any horizon any instrument could reach. The multiverse is, by construction, untestable. And here, the inversion writes itself. For years, naturalists have leveled a charge against those who infer a designer. They call it God of the Gaps, invoking an unseen intelligence to plug a hole in our knowledge. But consider what an infinite ensemble of unobservable universes really is, postulated for the sole purpose of explaining away a fine-tuning that would otherwise point to design. It is naturalism of the gaps, an unfalsifiable, unobservable entity invented precisely to avoid a conclusion the evidence suggests. The physicists George Ellis and Joe Silk saw the danger to science itself, and in 2014 they wrote a warning in the journal Nature, titled "Defend the Integrity of Physics." Attempts to exempt speculative theories of the universe from experimental verification, they wrote, undermine science. When the proposed alternative to design is itself untestable, unobservable, and self-undermining, the alternative has not defeated the design inference. It has conceded how strong that inference must be to require so desperate an escape. Notice, too, what the multiverse does not actually do, even if you grant it. Suppose there really is a universe-generating mechanism, eternal inflation, a cosmic landscape, whatever you like. That mechanism is not nothing. It is a structured, law-governed process, finely arranged to produce universes at all. Where did its laws come from? Why these meta-laws, capable of budding off cosmos after cosmos, rather than no laws or sterile ones. The multiverse does not end the regress of explanation. It adds one more link and hopes you will stop counting. Push the question back 1 universe, 10 universes, an infinity of universes, and the same question waits at every level. Why is there an ordered, generative reality at all, rather than nothing? An infinite chain of dependent causes explains nothing, because the whole chain, however long, still hangs unsupported. Only something that does not itself require a prior cause, something necessary, self-sufficient, eternal, can end the regress. The question is not whether such a thing exists. Both the theist and the eternal inflation theorist agree that something uncaused must underlie everything. The only question is what that something is. An unconscious, mindless mechanism that just happens to produce ordered, fine-tuned, law-governed, observer-permitting worlds, or an intelligent cause with the power, the knowledge, and the will to do so. The evidence of precision points to the second. Mindless mechanisms do not produce, without direction, the kind of order we are standing inside of. Now we come to the claim that gives this whole exploration its haunting name. The claim that time itself is an illusion, that your future already exists, that there is no genuine becoming, no open road ahead, no real choice, because everything already sits frozen in Platonia. We must be careful here, more careful than anywhere else, because two very different things have been bundled together under one phrase, and the examination depends on separating them. The first thing is the physics. The four-dimensional block, the relativity of simultaneity, the missing time in the Wheeler-DeWitt equation. None of that is under attack here. The geometry of relativity is among the best tested science we have, and I will not pretend otherwise. Nothing in an honest examination requires denying a single experiment. The second thing is the metaphysical leap, the jump from the equations have no time variable to therefore your sense of living, choosing and becoming is a lie, and the future is as fixed and unchangeable as the past. That leap is not physics, it is interpretation, and it is the leap we examine. Begin with the most famous piece of evidence for it. Einstein's line about the stubbornly persistent illusion of past, present and future. It is quoted endlessly as Einstein's considered scientific verdict that time is unreal. It was nothing of the kind. Those words come from a private letter of condolence, written in March of 1955 to the grieving family of his dead friend Michel Bessot. A letter in which a man facing his own death and mourning his oldest companion reached for comfort in the timeless vision of physics, the consoling thought that Bessot had not truly vanished. The physicists Carlo Rovelli and Tim Maudlin have both pointed out how badly this has been abused. A tender, personal consolation has been laundered into a hard physical result. Einstein did not prove time is an illusion in a letter of grief. He grasped at a hope. Building a metaphysics of frozen fatalism on those words is like reading a eulogy as a laboratory report. Now examine the leap itself on its merits. Does the missing time in the equations actually establish that becoming is unreal? George Ellis says no, and his objection is the most concrete in the whole debate. The static block, he argues, stands in profound contradiction with the world we actually inhabit, with chemistry, with biology, with the irreversible, one-directional flow of ordinary life. Cups shatter and never reassemble. The dead are not restored. You remember the past and not the future. Every process in your body, every reaction in every star runs one way and not the other. A theory that declares all of this a frozen illusion has not explained the arrow of time. It has denied the most universal feature of experience and called the denial a discovery. And recall the deep irony at the center of the timeless picture. Its own defenders, faced with the missing time, had to work feverishly to derive the flow of time back out of the static equations, the Page-Wouters mechanism, the thermal time hypothesis, the whole industry of explaining how time emerges. But you do not labor for decades to explain how an illusion arises. The very effort concedes that the flow of time is real enough, robust enough, undeniable enough to demand an explanation. You cannot in one breath call time an illusion and in the next devote your career to deriving it. One of those two attitudes is the honest one. Let me ground this in the most ordinary terms I can, because the everyday is where this claim either lives or dies. Picture a man building a house with his own hands. He has not yet laid the foundation. The future house exists only as possibility, as intention, as something that will be real only if he acts. Day by day he chooses this wall here, that window there, and each choice, once made, hardens into fixed, unchangeable fact, while the rest of the house remains open, unbuilt, genuinely undetermined. His past work is settled. His future work is not. The present is exactly where he stands, hammer in hand, converting open possibility into closed actuality. This is precisely George Ellis's growing block. A fixed past, an open future, a real and advancing present where decisions are made. And it matches your life so exactly that you have never once, in any real decision, behaved as though the alternative picture were true. Now watch where the frozen analogy breaks. The defender of Platonia must say that the house already exists, complete in the timeless landscape, that the builder's sense of choosing which wall to raise is an illusion baked into a single still frame, that his deliberation decides nothing because everything is already there. But here, the everyday picture simply refuses to bend, and the point where it refuses is the point where the claim fails. For if the builder's choices are illusions, if nothing is ever genuinely open, nothing genuinely decided, then so is every choice you have ever agonized over, every wrong you have ever resisted, every act of courage or cowardice you have ever performed. The frozen universe does not merely make time an illusion, it makes responsibility an illusion, deliberation a charade. the moral weight of a human life a trick of perspective on a static block. And no one, not Tegmark, not Barbour, not Gödel, actually lives this way. They argue, they revise, they choose their words, they hope to persuade you, as though the next moment were genuinely open and genuinely mattered. The theory is contradicted not in a laboratory, but in the conduct of the very people who hold it. A claim that cannot be lived, even by its own defenders, has told you something about itself. And consider what the open future, the real present, the genuine becoming actually fit. They fit a cosmos that is going somewhere, a creation unfolding in time, with a real beginning and a real direction, in which choices have weight because they are not yet made. And the moral life is not a frozen diagram, but a road genuinely walked. The flow of time you feel is not an embarrassment to be explained away. It may be exactly what it seems, the signature of a created order, brought into being and sustained, moment by moment, by a cause that is not itself trapped inside the block. A cause that is to time what the author is to the story, present at every page, yet bound by none of them. There is one last thread to draw tight, and it is the strangest, because it turns one of our timeless thinkers against the others. We saw that Tegmark would make you a computable mathematical structure, a pattern of information, in principle reproducible in any sufficiently powerful machine. But we also met Roger Penrose, who spent decades arguing, from Gödel's incompleteness theorems, that the human mind is not computable at all. That mathematical understanding does something no algorithm can do, something that steps outside any fixed set of rules to see a truth the rules cannot reach. Set those two beside each other and feel the collision. If Penrose is right, then you are not a piece of computable mathematics, because your own understanding outruns computation. The thing in you that grasps a mathematical truth is not itself a mere theorem being mechanically derived. And this points at the deepest gap of all, the one that no version of the mathematical universe has closed: consciousness. Suppose you had the complete mathematical description of a brain, every particle, every field, every equation, the whole structure laid out in Platonia, perfect and entire. You would still not have explained the simplest fact about that brain: that there is something it is like to be it, that it sees red, feels pain, tastes salt, suffers and loves. No equation, no matter how complete, has ever been shown to entail the existence of inner experience. Arrange unconscious quantities however you like, and nothing in the arrangement explains why the lights are on inside. Philosophers call this the hard problem of consciousness, and it remains exactly as hard as it ever was. A mathematical structure is by its nature a pattern of relationships, and a pattern of relationships, however intricate, is not obviously the kind of thing that can wake up and feel the morning. The fact that you are conscious, that there is an inner life reading these words, is the one fact about reality that pure mathematics seems constitutionally unable to capture. And it is precisely the fact that points beyond the merely material, toward a source of mind that is itself mind, not mechanism. So let us assemble the verdict, the way a prosecutor assembles a case after the witnesses have spoken. The claim was that the universe is a timeless mathematical structure that needs no maker. Under examination, that claim came apart in the hand. The mathematics that was supposed to replace a creator turned out to be causally inert, unable to bring itself into existence, requiring something to light it into a living world. The multiverse that was supposed to explain away fine-tuning turned out to be untestable, unable even to define its own probabilities, and self-undermining to the point of destroying the reason to believe it. The timelessness that was supposed to abolish becoming turned out to rest on a misread letter of grief, and to contradict the most universal features of the world we live in. And the mind that was supposed to be just another computable pattern turned out, on the testimony of one of the greatest mathematical physicists alive, to be the one thing in the cosmos that computation cannot capture. At every turn, the evidence that was offered to remove an intelligent cause, examined closely, pointed back toward one. What does it mean that the deepest mathematics of the cosmos is shot through with order, with information, with precision, tuned to one part in a number too vast to write, and that unconscious matter, left to itself, has never once been shown to produce such things without direction? It means that the question Platonia was built to silence is louder now than when we began. The universe is not less mysterious for being mathematical. It is more so. For mathematics is the language of mind. Equations are the kind of thing that thoughts are made of. And a cosmos written in that language, tuned with that precision, lit into actual existence and set flowing through real time toward real ends, reads, when you follow the evidence honestly, refusing the untestable escapes, not as the output of nothing, but as the work of a mind, eternal, uncaused, possessed of power beyond measure, knowledge beyond measure, and the will to decide. This is the part that stays with me. Not that the universe is made of math, that math is the kind of thing minds think, and we are standing inside a thought. Let me bring this exploration to a close. We began with a single missing letter, the absent T in the Wheeler-DeWitt equation, and followed it down into the strangest country in modern physics. We walked the block universe of Minkowski and Einstein, where past and future lie equally real. We entered Julian Barbour's Platonia, the timeless landscape of frozen nows, and Max Tegmark's mathematical universe, in which you yourself are said to be a structure of pure mathematics. We watched time vanish from the deepest equation, and saw the Page-Wouters mechanism try to coax it back from entanglement. We stood in Gödel's rotating universe, where the past can be revisited, and traced the holographic thread, Maldacena, Susskind, Wheeler's it from bit, toward a cosmos that may be made of information. And we heard the dissent, Lee Smolin insisting that time is the realest thing there is, his cosmological natural selection surviving the test of a pulsar weighed at the very edge it predicted. George Ellis growing his block one fixed moment at a time. Roger Penrose holding that the mind itself escapes all computation. And then we examined. We found that the timeless mathematical universe, for all its elegance, cannot account for its own existence, cannot test its own claims, cannot survive the Boltzmann brain logic it generates, and cannot capture the one fact each of us knows most intimately, that there is someone home behind the eyes. The mathematics is real, the precision is real, the order is real. But order is not self-made. Mathematics is not self-existent. And minds are not built out of equations that do not know they are being read. Follow the evidence where it actually leads, refusing the comfortable escapes that no experiment could ever check. And it does not terminate in a frozen, mindless structure. It terminates in an intelligent cause. Eternal and uncaused, the source of the order, the author of the law, present to every moment of a creation that genuinely flows. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And there is a door we kept passing but never fully opened. Again and again we spoke of the wave function of the universe and the hidden arena it is said to live in. Wheeler's superspace, the abstract space of every possible shape the cosmos could take. The true stage on which the timeless equation is written. We only glimpsed it here. If that arena stayed with you, if you want to stand inside the space where every possible universe is a single point, I have followed that thread much further. You will find where on the end screen now and in the description below. The mathematics, in the end, leaves us holding a question it cannot answer on its own. Why is there a real world to be described, rather than only the timeless possibility of one? Why is the cosmos written in the language of thought? John Wheeler, who gave us the wave function of the universe and the missing time inside it, spent his long life circling that very mystery. And near the end, he offered a line that belongs over the door of all of this. At the heart of everything, he said, is a question, not an answer. The equations are frozen, and time may be the deepest puzzle in physics. But you are not frozen. You are reading this in a moment that is genuinely now, making your way through a future that is genuinely open. Inside a universe whose precision and whose order ask, quietly and relentlessly, to be explained. Sit with the question tonight. It is the most important one there is. Good night.